section 2.1 and 2.2, page 3. So we're just beginning with a problem that asks us to find the derivative of a given function. In this case, we are not given a value for x, so we're going to be using the general equation 2.1b, which we had learned on the previous page, which said we're taking the limit as h goes to 0 of essentially the difference quotient, where we're starting from a point x and moving h steps, units, distance beyond it, ending at x plus h. So here I have repeated the formula that we just saw. Because the function was given as y equals, I'm using y prime notation, even though we're using f of x notation within the formula. So I need to swap out f of x with the actual equation I see where the input stays x. But before that, I need to take that exact same function and convert the input to the binomial x plus h. And again, I'm dividing by h where h equals 0, and I can't let h equal 0, so I still need to be writing the limit. What happens here is usually after this first step, there's something we can simplify. And although I could distribute the 5 to the binomial, it's not going to give me anything that's going to cancel off with an h in the denominator. So instead, I'm going to multiply that equation by 1. Well, 1 in its disguised form as the conjugate of the radicals on top so that I can remove those radicals. So right here, this term that I'm multiplying by, the top and the bottom are the same, but you'll notice we have a binomial of radicals with a subtraction. So the conjugate is the addition of those binomial radicals. And of course, the top and the bottom have to be the same. Don't forget, we chose the conjugate because if you have a binomial with a subtraction, a binomial with the addition, and whether you use FOIL distribution, the box method, you always get the first term squared minus the second term. And since our first term is a radical squared, it just causes the radical to go away. Same with our second term, squaring a square root eliminates the square root symbol. So I'm going to take this line and now replace it as the entire numerator for that problem. Here is my replaced numerator, and keep in mind the denominator ends up kind of messy with all this stuff, but it's okay, don't distribute. So I will distribute the 5 to the binomial. I will distribute the minus sign to the two right terms. And looking at the top only, I now am going to have a positive 5x, which is going to subtract off with that original 5x. I only distributed the 5 to the binomial, so I still have a positive 1 that is going to cancel with what is now a negative 1. They add to 0. So marking my like terms with similar symbols underneath, all that I'm left with in the numerator is the 5h. So the denominator is still this long, crazy piece, but when I only have the monomial of 5h in the numerator, I can cancel that h with the h in the denominator, the reason I didn't want to distribute it. And now I have a limit where it appears that plugging h into the denominator will not cause 0 in a denominator. So I've left the limit where it's possible to plug 0 in. Then I'm actually going to plug 0 in. Remember, h only, not x. And so the limit is obviously gone. This is just going to give me 5x plus 1. And what happens is, if you'll notice, I have 2 of the same radical. So I can combine like terms and say I have 2 of these, right? If I have m plus m, you would write 2m. That's essentially what we did, but we had radicals. Anybody who knows the the power rule, I'm getting out of control, the chain rule for taking derivatives, go do this off to the side and you'll notice that this is the answer. The last major concept to talk about on this page is a function and its derivative, but specifically the graphs of these. So what I'm going to do is first I'm going to find the derivative of a function. And then after that, once we have a derivative and its function, we can go ahead and sketch those. You'll notice I was not given a value for x. So just like the problem above, I'm going with the generic limit formula, where instead of setting x equal to a value, because I don't have a value for x, I'm setting h equal to 0. So where I've got my first function, I take the x squared plus 1, but make the input the binomial x plus h. Then basically the second term is always to copy the question identically as you see it. And keep in mind this is all over h as we take the limit as h goes to 0. I don't need to multiply by a conjugate, I just need to simplify. But don't forget, where we have a binomial squared, that really means the binomial times itself. And you can go ahead and work it out, but you'll find that this is the simplified version. So the green piece simplified to an expanded binomial plus 1, and the pink piece just had a negative sign distributed. This should allow all of the negative terms to cancel with some of the green terms, but there should usually be green terms that have h's left over, as you'll see in this line below. I still can't plug h equals 0 because I'll get a denominator, but now, since I have terms with h's in every term on the top, I can factor that h out, divide this one out to just leave me the 2x, divide this one out to leave me one of the two h's, so that I can cancel those h's, and now I can write an equation where I have limit as h goes to 0, and I do not have an h in the denominator. That wasn't an x, that was a no. So now I'm allowed to actually take the limit by letting h, not x, equal 0. And of course, I don't want the limit word phrasing in front anymore, and anything plus 0 is just itself. So we have now found the derivative is 2x. We're ready to talk about the graph of these. So we want to graph the function first. We were given x squared plus 1. Hopefully you recognize x squared means we have a parabola. The plus 1 is to shift up 1, right? If x was 0, I would have 0, 1. If x was 1, 1 squared is 1, I would have, here's 1, 2. But even if I plugged a negative 1 in, I'm still going to have a height of 2. So we can draw this parabola, which I've highlighted in yellow, to be my f function, f of x. Now we want to sketch the derivative. Keep in mind, this derivative is pretty easy to recognize, right? If we were looking at y equals mx plus b form, we can see that b is 0, so it passes through the x-axis at 0, and our slope is 2, which means we're going to rise up to run over 1, up to over 1, etc., until we get this green highlighted function of the derivative. Now, in this case, it wasn't too hard to sketch either of these, but we're going to end up with a lot more complex functions and derivatives that are more challenging to sketch. So here's the secrets to pick up for this. Anytime the original function has a horizontal tangent line, then the slope of that tangent line is going to be 0. That means the derivative is 0. So because I notice this horizontal tangent line at the bottom of my U shape right here, then it was at this spot where x equals 0 that my derivative has a height of 0. And if you notice, if you look at all the functions of the original graph highlighted in yellow, and you're just looking from negative infinity to 0, just this left half of the graph, you'll notice that this graph is decreasing this region, meaning all of these tangent lines have a negative sign, but negative tangent lines are a derivative. They are derivatives that are negative, which means derivatives below the x-axis. So as this graph was headed downward, if you want to think of that, my derivative, all of this, is below the x-axis. And then we have the reverse. As my graph of the original function increases on the right side of the line y equals 0, you'll notice that I may have all these positive tangent lines, so my derivative needs to be in the positive region where all the y values are positive for the graph. Hopefully that's clear. You'll see it in the next page in more detail.